So today's leak, or I guess it was yesterday's leak code problem, super hard for me. I was not able to do it, and I even had to watch a lot of stuff and spend a lot of time studying it, and it's still really tough for me. So I think this is going to just be a quick video. It's not a tutorial on how to do it at all. I just want to document my progress. This was one of those problems where I would never have gotten it. Like sometimes if it's like a hard problem or even a medium problem that I don't understand, if I spent like hours on it, I think I can do it, but I'm not going to record for hours. But this is one of the problems where even if you gave me like a whole day, hmm, I would not have thought of this solution. Okay, so just to preface this, um, there's this YouTuber Larry makes really good videos, from scratch. No, like looking at the solution. I really like his style. So this solution is his, and I just wanted to like talk about it, document like what it means to me. So okay, the question first is interesting, right? They want they give us like this like nums array with a k, and then we can only apply like k operations, so that we're limited to k operations. Our score starts at 1, and what does the score mean? The prime score of an integer x is how many like distinct prime factors are in x, and then we just want to keep multiplying our score k amount of times, and we want the maximum, so we want the best. So whenever we see maximum, it's a hint that we're going to have to use some sort of like greedy approach. um and that's about all that I could contribute to the problem. So now let's talk about the actual solution. Well, there's like three like major parts of this. The first part is just like pre-processing all prime factor scores. Okay, that's like a pretty big chunk of it. And then another chunk is like if we were given this array, we would want to see how like 8 has how many prime factors, right? Because we could process the prime factors in step 1. Now in step 2 is with that index, how many like sub arrays can we create where 8 is like the dominant one. And then to compute that, we need to compute like how many subarrays to the left of 8 and how many subarrays to the right can we use. And then if we multiply like the left and the right, that's going to be how many total possible subarrays where 8 or where this index is the most dominant, right? So we do that using um like a monotonic stack to process how many subarrays the current index can dominate dominate in. And then finally the third is kind of like this greedy approach where we take our number like 8. Wait, no, we don't take our number 8. Let me see. Yeah. So, okay, yeah, we do take these numbers and we kind of sort them, but then we also keep track of how many subarrays they were a part of. And that would be, and then we can find the max thing. So when we have a greedy approach, we want to sort by greatest, and then we're sorting x, and then we're doing like the left times the right, which is the total number of possibilities. And then note that x is just going to be like nums of I, just like a some sort of number inside of nums of I. So these three main parts. So the first part of computing, we use the sieve thing, which is like really good for computing all prime numbers very efficiently. The whole idea is that um, if we were on 2, let's just say, we could do 2 uh, plus 2, which is 4, plus 2 is 6, plus 2 is 8, 10, 12. We could keep going all the way to this like max number. And every time we go all the way up, we just say that it's not a prime anymore, right? Because it's a factor of 2 now. And then we could just update our factors to say, hey, now that factor at 2 or that, or not 2, that factor at 4, that factor at 6, 8, 10, those are all going to have one factor now, right? And that factor is 2. Then later, like if we were at factors at like 10, um, factors at 10 would, or sorry, if the prime was 5, right? So then s would be 10 because 5 plus 5 is 10. So then our factors at 10 would go up another one. And now factors of 10 would be 2, right? F of 10 would be equal to 2. And what would those two things be? It would be a 2 from before, right? 2, 4, 6, 8, 10. And then also it'd be a 5 from 5 plus 5 is 10. So then you could see how 10 has 2 prime factors. So that's how we're going to do this. And we just keep going all the way to the max number. And what we're doing is we're pre-processing the score. So we don't really care about this prime thing. This is only to help us build. What we really care about is the factors, right? The number of prime factors. So when we actually do this problem, we can just set the number of prime factors for x in nums, because x is going to be like this, right? Like 8, 3, 9, 3, 8. These all associate with prime factors that have been pre-computed. So this all of a sudden is going to turn, our p is going to turn into, what is the prime factor of 8? They say, right? Wait, no, they don't say. Just 1. 3 is just 1. 9 is just 1. 3 is just 1. And 8 is just 1. I guess this problem's not super helpful for this example, but you can see that p isn't the nums. What it is it's the number of prime factors given nums. So then this is where we now do our monotonic stack, where we just try to find, like, if we're at this index, how many to the left does this index dominate, and then how many to the right. And then something to note is that if this was like a 3 and this was a 3 and we go here, we can't dominate anything to the right, right? Because the 3, if there's a tie, we have to take the minimum. So there's like some things that we need to modify. For example, if we're thinking about doing the left, all we need to do is make sure that it's less than. But then when we do the right, we have to do less than or equal to. So it's some like nuanced stuff in there. But I'm not going to go through this. I still need to study it more. But some sort of monotonic stack to help you determine how many to the left can we use, how many subarrays to the right can this index use. Then when we multiply them, so we could zip them together, nums left and right, then we could just append the nums with the left times right, right? So left times right represents the number of subarrays that this x can be a part of. Now, when we sort it, and we want to sort it by the max first, so that's why we reverse it, we can start looking at the best thing, right? X for x in answer. So x is going to be, since it's sorted, x is going to be like the best thing. Now, how many times can we do it? We can do it L times R, which is C, because we're unpacking it, right? We can do it C times. So, but what if we can use it C times, and what if C is super big, but our K is very limited? We have to just choose the minimum of C or K, right? And that's what we're going to multiply to our score, is we're going to say X times how many times to use, right? So like if we could use it 5 times, it would be X times X times X times X times X, which is just X to the power of the minimum of C or K. That's why we do this, and then make sure to mod it. Then we like mod the score as well. That's just part of the result because it could be super large. And then since we used up this many operations, right, we have to subtract that from K. If K ever dips below 0, we know that we ran out of operations, so we could just exit this for loop, and then we could just return the score mod by the original mod. So yeah, if you run this, it's quite efficient. Um, I was not able to get this problem on my own at all. This is just copied from Larry's code. I'll link his video below. I thought it was very helpful. But that being said, um, it makes sense, right? There's three main parts: pre-process all the prime factors, use monotonic stack to find at your index how many subarrays to the left and to the right of it can that index be a part of. And then there's this whole greedy aspect where we're just sorting the numbers um, with those like total number of subarrays so that we can start adding to our score. Um, but yeah, that's about it. And yeah, see you next video.